Before I proceed further, in case of Poisson's and Laplace's equation, I would like to specify two types of medium. Homogeneous, actually two characteristics of one particular medium, which is one characteristic is homogeneity, other characteristic is isotropic. Now, suppose I am standing on this white plane. If this is me and if this is a charge distribution, then if I place myself here, the medium property I can experience is the same if I switch my position over here. Then the medium is called homogeneous medium. Now, what happens in case of isotropic medium? Isotropic medium means the properties of the medium does not depend on the direction I go. Suppose these two are the charge distributions. Now the interaction between these two types of charge distribution at this place is same if the position is just switched over, which means the interaction does not depend on the direction of the medium. This is called isotropic medium. We will write Laplace's equation and Poisson's equation. We will derive Laplace's and Poisson's equation in case of homogeneous, static and isotropic medium. Till now we have actually obtained this relation. There is a simple relationship which stays between D and electric field E. Now, for example, vacuum is also homogeneous medium. Now, this is the relation between the D and E. These two are constants epsilon 0, epsilon r. So, divergence of D equal to rho V, and this epsilon 0, epsilon r product can be taken outside of the operation. So, epsilon 0, epsilon r divergence of E is equal to rho V, the volume charge density. Together I write this constant, this product of the constant as epsilon. So it's epsilon divergence of E equal to rho V. So divergence of E equal to rho V by epsilon. If in case of a free space, epsilon is replaced by epsilon 0. In case of free space, we can replace epsilon by epsilon 0. And we obtain the Gauss's law for free space. Now we know this relation that electric field can be obtained from the gradient of the potential, scalar potential itself. And for divergence of E equal to rho V by epsilon 0, which is the Gauss's law, we just put E equal to this relation on the Gauss's law, in the Gauss's law, and the left hand side is actually a new operator, and the operator looks like this. If we calculate the left hand side only, this gradient of V is nothing but it's a vector quantity, because this is a vector operator. It is operating on a scalar function, so it gives us a vector. And del of V is this one, and the del operator itself looks like this. So from the dot product of these two things, I have obtained this relation. This is nothing but del square of V. V is the potential here, and del square is del 2 del x square, del 2 del y square, del 2 del z square, which is called the Laplacian, and the Laplacian is obtained in the Cartesian coordinate system. So from the left hand side of the Gauss's law, we have obtained del square of V equal to minus rho V by epsilon 0. This negative sign comes from this relation, and this is what we call the Poisson's equation. Now if we consider that rho V equal to 0, that there is no charge distribution is there in the medium, so right hand side becomes 0, and we obtain del square of V equal to 0, which is called the Laplace's equation. Why these equations are important? Suppose the charge distribution is specified, so from the charge distribution we can obtain potential, and from the potential we can using you can easily obtain the electric field by using this relation. So these two equations are actually source equation in electrostatics. And what is the significance of this relation? This relationship tells us that electric field can be obtained from the charge distribution. That is, charge distribution is something which causes the electric field. This is electrostatics. So we have actually derived two source equations, Poisson's and Laplace's. Why these are called source equations? Because they are actually give us a path, a route to find out the potential and hence the electric field. So actually, when we have static charge distribution, we have electric field, and that is electrostatics. But when we have moving charge, that is current, we have magnetostatics. And we know from electrodynamics that if electric field varies, it produces a magnetic field, and if a magnetic field changes with time, that produces electric field. Now what I'm just give you a fragments of how these source equations are important. Now suppose we have a CRT, a cathode ray tube. We have two electrodes, a positive one and negative one. Now we do not have any knowledge of the potential distribution between these two electrodes. We know the potentials at these two terminal points. So this is as we know the potential at these points, so that is the boundary condition that we know. So if we know the potential at the boundaries, from that we can assume the charge distribution, because inside CRT we do not have any idea of how the charge is distributed, and hence we do not have the idea that how the potential is distributed. So from this kind of equations we can have a rough knowledge about the potential from these boundary conditions, and hence we can get an idea about the field also. We have learned the point form of Gauss's law. This is the point form of Gauss's law. This rho is the source, that is the charge density, which gives rise to the potential and the electric field. And this del dot D, we have learnt about the divergence. This is the vector operation of divergence. Now we will consider this equation for a few cases. For example, let us take this case, this problem, where the D field is along z-axis only. We have chosen the Cartesian coordinate system, but here we have also chosen that D has no component along x and y. It is distributed only along z direction. So if I consider this direction as the z direction and this as x and this is somewhere y, then the D field is only along this direction. There is no field along this direction or any direction along perpendicular to this copy. So here is the two-dimensional picture of what I have just said. Now suppose as D equal to k of z, k is a constant. This is the unit vector along z axis. So divergence of D gives me equal to 0 because k is a constant. So what is the meaning of this divergence of D equal to 0? Now the D field is distributed like this. Now if we consider a closed surface here, if we put a closed surface here which has enclosed some of the D field lines. So for this closed surface with del V volume, if we try to evaluate this integration, now this numerator is evidently equal to 0, because if we look into this closed surface, number of field lines going inside the surface is equal to number of field lines going out of the surface. So there is a balancing of flux for this closed surface. Now for Cartesian coordinate, this is true. What if we take a cylindrical coordinate? Now if we consider a cylindrical surface, a cylindrical closed surface, the same thing applies here too. The balancing of flux is also applicable for this cylindrical coordinates. I mean, this is not XYZ. So as the amount of flux going inside is equal to amount of flux going outside. And what is the conclusion of this is, we can conclude from this result that no charge is actually enclosed by this closed surface. That's why if we take a point and if we imagine a volume surrounding the point, if we imagine a surface surrounding this point, and if we just shrink this volume, so this divergence of D becomes 0, which is the significance that no charge is enclosed by this small surface. Now what if a point charge is considered? Suppose I have a point charge Q. This charge Q is situated at the origin of the coordinate system. As this is a point charge, it's a plus charge, so field lines are going outward, and these field lines look like this. It will falls off as 1 by r square. Now if I just take this one field line here, I have just zoomed this field line, for example. Now I cannot take a bigger surface like this, a bigger circle like this. Suppose I take a very big circle like this. So the D field at one point, at one side of the surface is very much different from the D field at other size on the surface of that circle. So I cannot take that bigger circle. So for this type of circle, I mean where in the limiting case, this shrinks to a very small volume. Divergence of D equal to 0, provided this circle does not enclose the origin, because at the origin the charge Q is situated. And this divergence of D is equal to 0 at any point except the origin, because origin has the charge Q.